This is Carl. Carl, like all carbon-based mammals on this planet, is a machine made out of clockwork meat. Uncountable microscopic machines sloshing around and working together to allow him to sit on the couch and eat crinkle fries while watching a documentary about endangered parakeets. Like all machines, though, things can go wrong, and they need repair. The problem is that unlike the usual kind of clockwork made out of brass and steel, living beings protest a lot if you attempt to open them up and look around on the inside to see what's wrong. And don't even get me started on the mess. So humanity needed a way to peer into our bodies without making holes. That way we can decide if the inner bits need manual adjustment or if the ailment simply needs the right medicines and time to heal. Unfortunately, unlike some species of fish or frogs, humans aren't generally transparent, and while it's technically possible to shine enough light on a body to get a little bit of a peek inside, visible light just doesn't penetrate flesh well. Normally, if you put your hand in front of a light bulb, you simply cast a shadow, which, while great for shadow puppets, doesn't tell you anything about what's inside. But instead of a normal light bulb, we're going to try this very strange looking one. If I put something in its path, it too casts a shadow, but something looks odd. Instead of plain darkness, the inner workings of this gadget are projected onto the floor, as if its soul has been cast out of it for us to see. As you may have guessed, this special light bulb is an X-ray tube, and it also happens to be probably one of the most dangerous things I have in the lab, even if it doesn't seem like it at first. The shadow we're seeing is from X-ray light partially penetrating this Geiger counter and casting an image onto a special fluorescent screen that converts the X-rays into visible light. We made a video a little while ago playing with this tube and managed to take some incredible images. Of course, we X-rayed a rat and various bits of tech, amongst other things. Probably my favorite, though, was this X-ray of the Egyptian mummy that we made a few years ago. We spent 9 months carefully preparing this mummy, and it was amazing to see all the little details we included show up on the X-ray. For example, right here is one of the many amulets we embedded in the wrappings. And if you haven't seen that video, or the follow-up we made recently, be sure to check those out after this. But there was a problem with our last foray into the world of spicy light bulbs. Well, okay, there was a lot of problems. For one, it was incredibly jank and pretty much just thrown together, which, when large quantities of radiation are involved, that's famously not a good plan. In order to be safe, we had built a thin lead wall and an extremely long remote control line so we could operate it safely. Where we were standing, no radiation was ever detected. However, that still meant we were blasting X-rays into the open, which I'm told is not ideal. Safety aside, even just powering the tube was done in the most hack way possible. Our initial high-voltage source was literally a cheap plasma lighter that was then used to power a voltage multiplier. This meant it had to be regularly recharged and would reliably run out of battery right when we were in the middle of a test. On top of that, the actual output was incredibly variable, being really strong when at max charge for about 4 seconds before fading. And that's not even mentioning how we turned it on. Triggering it was accomplished by a very long remote control wire that made a solenoid physically push the ignition button. All told, not very elegant. The final issue was that the X-rays we took were just that, simple X-ray images. But there's a lot more that you can do with an X-ray source like this, and the images, even the nice ones, were contaminated with a lot of stray light. Today, we're going to rework all of this and build a system that is safe to use and has way more functionality. And when it's done, there's a lot of things we're going to scan and take a peek inside. First up, if we want to keep firing off the tube, no matter what we want to do with it, it has to be moved to a lead-lined box so all the spicy stays on the inside. That way, we can take as many X-rays as we want. Then, we'll completely overhaul the power system and build in a bunch of automation, which will make our images brighter, more consistent, and controllable from a laptop. With those fixes complete, we can start adding upgrades. The main one for today will be a rotary platform to put objects on, and with that one small change, our X-ray box becomes a fully functional CT scanner. A CT or CAT scanner is one of two main kinds of magic science donut that they use at a hospital when something has gone very wrong inside your body. Maybe you've got a stone growing somewhere it shouldn't, or you slipped and find yourself with a new resident in your upper colon. No matter the case, a CT can perfectly pinpoint it so surgeons know what steps to take next. They work by taking many X-ray images all the way around a subject, then using a bunch of math to turn that data into a 3D model of the patient. Normally, they work by having an X-ray emitter and X-ray sensors whipping around a patient at a speed that frankly makes you deeply appreciate the thin plastic cover that's usually on the machine. The hospital-based scanners work this way because the alternative, where you mount a patient to a roasting spit and spin them around, is generally frowned upon, especially if you're going to be whipping them around at the usual CT speeds. After all, no one wants to clean puke out of $1 million machine on the regular. But that might be a novel method for foreign body removal.
I want a proctologist standing by. What? You heard me. Best one you can find.
However, if you're not working with a human and are just going to be scanning objects, it's totally fine to rotate the object instead of the scanning head. The math that makes all this work doesn't actually care which is moving, just so long as the motion is smooth and consistent. And you don't need to have it moving fast either. The medical ones are spinning so quickly to help reduce the amount of radiation a patient is exposed to, and get the scan over as quickly as possible. But a Furby can't get cancer from being irradiated, I think. So in our case, we don't need speed either. There's more we want to do with this box, like X-ray fluorescence and diffraction, and we've already ordered a bunch of pieces to upgrade this further in another video we're already working on. But we'll talk more about that near the end of the video. For now, there is lots to do, so we should get building. Then we can move on to scanning. Now, truth be told, we are not the first people to build a CT scanner on YouTube. Both Applied Science and Hyperspace Pirate built versions of CT scanners and made excellent videos on their respective builds that I would highly recommend. However, we designed ours to be unique in that you can actually stand next to the thing while it's running without it harming you, instead of having to give it a 30-foot safety distance. Yes, that is a low bar, but we specifically wanted to demonstrate what it takes to work with things like this safely. So let's start with the box. We know we want it to be lead lined, but lead is a very silly material and one of the goofier elements in my opinion. It is incredibly bendy, and working with it is sort of like handling very heavy plasticine. It bends and molds, and it takes a line absolutely beautifully, making marking out cuts a breeze, and normal scissors are all that's needed to make those cuts. But that ductility comes at the cost of literally any structural stability. And even thick plates bend and flop. So unless we wanted to spend an insane amount of money on enough lead that we could cast it into bricks and stack them, the lead itself can't be used to make the walls of the box, and we're going to need to support them by something else. Now, there are a lot of strange things that you can buy on the internet, but prefabricated CT scanner walls probably wasn't something you'd expect. And yet, inside this box is exactly that. A big part of the reason we were able to do this project is because of the sponsor of this video, PCBWay. You may know, or at least suspect from the name, that they make PCBs. And sure enough, they do, and we'll show you our shiny new boards, also from them, in just a moment. But they also have a variety of machining and 3D printing services. So we asked them to CNC some nylon plates that we could use to build our scanner box. And in hardly any time, these crates full of beautifully machined plates arrived. Everything was packed super well, so it took a little bit of time to unwrap everything, but every single piece was perfect and came out to spec. All we needed to do ourselves is build an internal frame to mount the plates to, and of course, add the lead. The frame was made from extruded aluminum, which was intended to make it easy to bolt all the pieces together. The plates that bolt onto the frame are made as a sandwich. There's a smaller internal plate, a layer of lead, and then a larger external plate. And of course a bunch of bolts will press them together so the lead can't move. In the name of saving some money, we had initially bought lead ingots with the intention of casting our own sheets. You used to be able to buy rolls of lead at pretty much any hardware store, but lead use in Canada has been phased out for decades, so the only lead sheeting available came at a huge markup. We had picked up this big cast iron griddle to use as a mold, as well as some flux and a non-stick coating meant for bullet molds. But after melting a pot of lead and starting the pour, we realized three things. First, the cast iron wasn't actually flat and actually bows out in the middle. Second, it's a massive heatsink that causes the lead to solidify the second it touches it. But worst of all, lead's surface tension is absurd, and getting thin layers like this was just not going to happen. Eventually, after wasting some more time trying to make this work, we mostly gave up and just ordered the more expensive pre-made sheet lead. However, I did manage to figure out a method and produce 2 plates that will be used for the hottest parts of the box. The trick is to use a torch to selectively melt and move the lead to where you need it, and then let it rapidly set so it stops moving, and also using enough extra lead to compete with its insane surface tension. Then, once it was cast, I still had to bust out the anvil and hammers to even it out and stretch or thin the metal to fill any gaps. This was a ton of physical work, and lead is so bloody heavy and floppy that you have to fight it a lot to make it behave. Though, thanks to its softness, you can use things like chisels to cut it like butter if it gets too thick for scissors or snips. Ironically, this video ended up being an accidental continuation of our exploration of different metals. We just did a video on copper and bronze alloys, and another video on iron and steel. So I suppose this is going to count as our lead video. And lead was likely the first metal that humans ever mastered. Anyway, even for the pre-made sheet lead, there was still a lot to do. I had to lay out the sheets so that they were at least 3 layers thick, and there was a slight overhang on certain edges. This way, once all the panels are assembled, we won't have leaks along the seams and can have the lead overlap. Once the sheets were laid out, they needed to be adhered together, and while I suppose I could have used glue, lead melts really easily, so I just welded the sheets together using a simple butane torch. Again, this took some practice to figure out, and I needed to add extra lead to account for the surface tension. And before you ask, yes, we tried a stained glass soldering iron, but there's just too much lead. The iron couldn't get hot enough to deal with the immense thermal mass. Once all the pieces were welded together and tidied up with a hammer, we could assemble the sandwich and punch out the holes. Initially, we had tried pre-cutting the holes with a punch before the sandwich, but getting everything perfect was very hard when the lead shifts around. So punching after assembly and using the bolts to hold it in place worked way better. But that's the basic process. Lay out the sheets, spot weld by sneaking a rock slab under the sheets so we don't damage the nylon, then punching and bolting it all together. This took literally days, as it was hot, heavy, exhausting work. And to not end up as full of lead as your average boomer, I had to wear a respirator and gloves, as well as, frankly, a lot of hand washing just to be safe. Honestly though, lead, for all its flaws, would probably be my favorite element if it wasn't so bloody toxic. It is so cool to work with, and I can absolutely see why the Romans loved it. While I was working on the panels, the rest of the team was hard at work on the electrical side of the machine, as well as getting all the missing pieces 3D printed or ordered. There are a variety of special brackets we needed to hold the various components together, and we needed boxes to house the various electrical boards that'll make the machine work. So let's talk about the electronics for a bit. As I mentioned earlier, the boards were made by PCBWay, but more than that, they arrived pre-assembled with most of the components already installed. And both boards looked beautiful right out of the box. However, we only had PCBWay mount the SMD components, as all the big chunkies we saved for mounting ourselves. If you need PCBs, parts CNC machined, or 3D printed, the first 200 people to use the coupon code PCBWay Thought Emporium 10 will get $10 off their order. Just follow the link in the description to get started making things today. So what are these 2 boards anyway? The first is the brain of the machine. It's got 2 voltage regulators that convert the incoming 120 volts AC into 12 and 5 volts DC, respectively. This is to provide power to a Raspberry Pi, which will allow us to control everything, as well as a stepper motor and the filament of the X-ray tube. It also has a huge number of safety interlocks that all need to be activated before it'll allow the tube to be energized. Finally, it has the ability to trigger the DSLR that we're going to be using to capture the X-rays, so the entire process is automated. X-rays are normally invisible, but using special fluorescent screens, we can convert the X-rays to visible light that we can actually take a picture of. The camera is going to be outside of the box, and the screen and a mirror will be inside the box. This way, we don't expose the camera's sensor to the radiation and ruin the image. And that way we can bounce the visible light up and out of the box safely. The safety interlocks will mostly be limit switches that will guarantee that the door of the machine is closed properly before any X-rays are produced. But one of the interlocks is controlled via an optical fiber and this remote. This way, we can be far away from the machine and arm or disarm it safely. It's just one last layer of protection. Even though we're building the machine to be safe enough to stand next to, we're still not going to while it's running, just out of an abundance of caution. We also fully expect that there's going to be some initial leaks which will have to be plugged with extra lead. So until every leak and hole is plugged, we will be far away from the machine while it runs. Though in our testing, the lead walls did an amazing job of keeping the radiation in the box, with only a few tiny leaks. Once the system is fully armed, we can then control it remotely from a laptop that will send instructions to the Pi. And when we tell it to take an X-ray, the board will flip this relay, which energizes the second board. Well, okay, strictly speaking, it sends power to this power supply, but then that powers the second board. This board is a really beefy ZVS driver. You can get little dinky ZVS drivers on Amazon, but we've killed so many of them over the years that we built one to be much closer to indestructible. This takes the DC voltage coming from the power supply and turns it into high-frequency AC, which is needed to power this flyback transformer. Flyback transformers are air core transformers that can take a relatively small voltage and, in this case, step it up to about 10,000 volts, though you can get them to output a lot more. They're the same sort of transformer that used to be used to make CRT TVs. Now, if we were building a TV, this would be enough voltage, but an X-ray tube like ours needs even more voltage still. Specifically, this tube runs at about 70,000 volts. To get that voltage high enough, we're going to be using what's called a CW multiplier, which is a special circuit made out of capacitors and diodes that will boost the incoming 10,000 volts AC to 80,000 volts DC. And yes, I do realize that the AC to DC to AC to DC is a little bit like wet the dries, then dry the wets, then wet the dries, then dry the wets, but I digress. Last time, we had used what was called a half-wave multiplier, which looks like this. But this time, in the name of doing things properly, we upgraded to a full-wave multiplier, which will give us a smoother and more stable output. Because of the sheer amount of voltage involved, this needs to be potted in epoxy so none of the magic pixies can escape and fry one of the components. After using a torch to pop all the bubbles and make it look pretty, this was allowed to cure overnight. Alright, with the panels prepared and electronics ready to go, we could start assembling it together. But that was easier said than done in many directions. It turns out, and this may come as a shock, lead is quite heavy. I know, blistering insight. But the weight meant that everything shifted around, and supporting the panels while trying to get the bolts to cooperate felt a bit like doing surgery. But I don't mean brain surgery, more like orthosurgery, as in requiring the use of a very large hammer to coerce the panels into place. That and the odd clamp or shim to bend things into alignment. Thankfully, the machined nylon is very strong and could bear the load and, frankly, a light beating. After a full day of beating and pushing and effort, we managed to get all the panels mounted, only to find that now the door doesn't fit. So that had to be thrown onto the bandsaw to trim a 1/4 inch off the top, which was not the prettiest solution, but thankfully it isn't particularly visible. But that's the main box done. For the electronics, everything got custom boxes and cables to hook everything up. And initially, we had spent some time drilling and tapping some nice holes to bolt all the components to the main box. But the first time we went to fire it up, we were reminded of just how angry the pixies are in a 70,000 volt power line. Keep in mind, at these voltages, the electrons are quite happy to jump more than an inch through the air if they find a path to ground. So keeping them moving to where we wanted them was tricky. I'll save you having to watch an entire week of debugging and struggle, but we ended up having to put extra insulation on literally every wire. This meant putting the wires into silicone tubing to act as a thick insulator. We also removed the bolts and then added a double layer of garolite and foam core under each of the electrical components, as we realized that some amount of voltage had somehow managed to find its way into the lead layer. So all of the bolts that we'd been using to mount things had somehow become energized. With the boards isolated, we could ground out the frame in the lead, and with all the wires in their silicone sheaths, the X-ray tube itself was actually isolated, so all of the power was forced to go through the tube properly. Not only did this solve our arcing problem and stop cooking our control boards, it made the X-ray way brighter, so we also only needed half the exposure time to get just as nice of an image, which was a very unexpected but appreciated boon. With all that working, the system is now ready for a scan.
What should we point it at first?
I don't know. Try it on me. Ow! My sperm!
Now, the temptation was, of course, to scan pretty much anything that wasn't nailed down in the lab, but we put together a small collection of stuff to start with today. We also stopped by a local grocery store to pick up a few critters and fruit and other items to scan. Though the look on the slightly flustered cashier when we attempted to buy a single walnut was absolutely priceless. Speaking of which, it's as good a place to start as any. We propped up our single walnut on some florist's foam, which is so light that it's basically transparent on the X-ray. This makes the walnut appear to be floating in midair and gives us a nice 360-degree view of it. Ironically, this may have actually been our most successful scan of the day, as not only did the images come out clean, we could clearly see the walnut meat. And when we converted it to 3D, the detail was preserved remarkably well. Now I can slice through the walnut however I wish. I suppose this is one way to pick the good walnuts from the bad ones, certainly easier than an army of specially trained squirrels. Though not all of our foods worked this well. We tried a pomegranate and a plum, only to find that water seems to be particularly good at absorbing this specific frequency of X-ray light. After all, this is a dental X-ray tube meant to shoot through only the thinnest bit of flesh. So both came out as kind of round black blobs. I was really hoping to see the seeds or a pit, but no luck. Eventually, we're going to sub out this tube for one that runs at a higher voltage and can produce X-rays that aren't stopped as easily by water. Though, if the object is thin enough, you can still get a decent image even if it's wet. For example, this slightly stinky fish. It took us a few days from the time of buying the fish to the time of scanning the fish, so it had to be left in its plastic bag as it was definitely starting to go bad. But thankfully, X-rays don't care about thin plastic, and you only really see the bag at specific angles. In the meantime, we got a pretty nice scan. Now, something you're going to notice in the results of our scans is that the images are clear and crisp, but the 3D rendering is quite a bit noisy, and sometimes we lose a lot of detail. With the fish, for example, we do see the bones, but the internal organs are basically impossible to see other than the swim bladder, and even cleanly separating flesh from bone in the scan is kind of hard. The issue is that we're using the most basic form of back projection to convert the images into 3D. There are much more competent programs that'll do a better job of this, but we went with the easiest option to get us started. It means that none of these scans are going to be high enough resolution to be worth, say, 3D printing, but they do still give a lot of information about what's going on inside a scanned item. It's just one more thing to address in the upgrade video. Between processing errors and water attenuation, not all of our scans worked. Much like the plum, a lobster turned out to be way too dense and thick, so all we got was the impression of a lobster and definitely no internal detail. But some things worked perfectly. We picked up a Matryoshka doll set, and we could perfectly see inside and count the layers, and the 3D model sliced incredibly well. We also chose a skull from my collection, and it worked beautifully. We can even see the shape of the brain that was left as an impression on the pattern of bone growth inside the skull. And even on 3D, it slices pretty well. Of course, we also had to scan a light bulb, but the bulb shifted partway through the scan, which left a bit of a weird phantom. Removing those bad frames gave us a more normal-looking bulb, but at the cost of more noise and less detail. Also, since this is a cat scan, we had to scan at least one cat. I found this kitten plushie next to your mom's bed, and when we scanned it, we found that she'd been hiding a rocket ship inside. I wonder why she never mentioned her love of space before. Odd. Probably the one I was the most excited for, though, was a Furby. These mechanical monstrosities have haunted my nightmares for decades, and while I've seen many a skinned Furby in my day, I've never taken a look to see if they're as haunted on the inside as they initially appear. Turns out, mechanically, they're actually pretty simple these days. I'm going to redo this scan with an older model to see how the mechanism has changed over time. But on the 3D, we can actually see all the nuts and bolts and springs really clearly. But again, we're having some issues separating the soft plastic parts from the background noise. Though, note that the ears look particularly dark, and that's because the plastic has been doped with a glow-in-the-dark powder that also happens to add a lot of contrast on an X-ray. Finally, a few bits of tech to round things off. Since our best picture from last time was a Geiger counter, of course we had to scan it again. This one actually worked pretty well, and you can actually see the filament wire inside the Geiger tube itself, though a lot of the electronics in the middle are a little bit hard to see. One way we can improve the scan quality is to simply take more images. We're currently taking 64 and moving the object at about 5.625 degrees per image. But in the future, we could set this to something like 300 or 1000, and that should tease out a lot more detail, not to mention making the math work better even without extra filters. Just to try out the concept, for our final scan, let's compare between a standard 64 image set and a 360 image set. For this, we're going to be using an old Walkman CD player. And yes, even us just having this immediately dates us as old, but I'm going to try not to think about it. Anyway, here is the normal 64 image scan. Now, here it is again with the full 360. We see much more detail, and everything is much sharper. But that's pretty much it for today's experiments. As I said, we're going to be back very shortly with upgrades to the machine. The most immediate upgrade will be the addition of some X-ray lenses that will allow us to perform X-ray diffraction experiments. There's a very famous X-ray image that is probably one of the most important in biology history, and I've wanted to replicate it for many years. Beyond that, if we add in an X-ray probe that can measure the energy of the X-rays after they strike a sample, we can also get the machine to do X-ray fluorescence measurements. This technique allows you to stick a sample in the beam and get back information about what the elemental composition is of the sample. It's often used for assaying ores to see what metals they contain. Finally, with a lead-lined box that is fully radiation sealed, there is one last thing we can try. There are alternative X-ray sources that are meant to basically be left on. They're less penetrating than the X-rays we used, but still have more than enough energy to discolor crystals and make salt turn orange. It can also be used for mutation experiments, and we can explore how radiation can allow us to genetically modify plants. All told, lots of exciting follow-ups, and of course, there are so many more things that we want to scan, so be sure to keep an eye out for many shorts in the near future. And if there's something specific you want to see us scan, let us know. Also, if you happen to know a better way to do the back projection, be it a specific method or piece of software, do let us know in the comments. I know we didn't really get into the math in this video, but that's mainly because I assume the method is going to change. So rather than waste time today, I can just explain whatever process we end up settling on to improve this. But with that, we come to the end of this video. As always, a special thanks to our amazing patrons that make these videos possible. Patrons get access to our exclusive Discord channel, and very soon will get the special ability to ask us questions during our podcast series. So if that's interesting to you, or you'd just like to help keep the flow of science videos coming, there's some links below. That's all for now, and we'll see you next time.